But this half hour we're going to show you some extraordinary images of space, and to do them justice really you need to see them. Across the James Webb Space Telescope, the most advanced observational tool ever launched into space, has pushed the boundaries of human knowledge once again. Recently it delivered astonishing images and data from a region lying at the very edge of the observable universe. This monumental discovery marks a new chapter in cosmology, revealing sights never before imagined and offering a tantalizing glimpse into the infancy of the cosmos, a realm formed less than a few 100 million years after the Big Bang itself. What the telescope has uncovered is far more than a snapshot of the distant past. It's a revelation that could rewrite the foundational assumptions of astrophysics and cosmology. Before we start, smash the like and subscribe buttons for more updates. For decades, the edge of the observable universe has remained a theoretical boundary, a horizon formed by the limits of light that has had enough time to travel to Earth since the universe began. What lay beyond it was anyone's guess. Hubble's observations had previously taken us far, allowing astronomers to peer into the early universe, but even it had limitations in terms of resolution and wavelength coverage. The James Webb Space Telescope, with its powerful infrared capabilities and enormous mirror, was designed to break through these limitations. With its recent observations, it has done just that, offering humanity an unprecedented peek at the very limits of time and space. In a groundbreaking observation campaign that lasted weeks, Webb focused on a seemingly empty region of sky deep in the constellation Phorax. What emerged from the darkness was a collection of ancient compact galaxies, some of them possibly protogalaxies, glowing faintly from over 13.5 billion years ago. These were among the first structures to form after the Big Bang, existing during the mysterious era known as the Cosmic Dawn. What made these galaxies so significant wasn't just their age or distance, but their structure and brightness. They appeared too evolved, too massive, and too luminous for the epoch in which they were found, challenging the existing timeline of cosmic evolution. This challenge has sent shockwaves through the astrophysics community. For years, the standard model of cosmology has suggested that the earliest galaxies formed gradually over hundreds of millions of years through the slow accumulation of gas and dark matter. The Webb findings, however, suggest that some of these galaxies were forming stars at a blistering pace, producing hundreds of solar masses per year, far faster than previously expected for the time. This discovery has raised the tantalizing possibility that either star formation in the early universe occurred through unknown mechanisms, or that our understanding of dark matter, cosmic inflation, or even the Big Bang itself may be incomplete or flawed. One of the most striking features revealed in the data was a cluster of extremely redshifted galaxies, their light stretched to infrared wavelengths by the expansion of the universe. These galaxies are not just old, they are fundamentally different from the nearby galaxies we see today. Some of them appear to have supermassive black holes already in their cores, which opens another cosmic mystery. How could such colossal black holes form so quickly after the universe's birth? Conventional models require vast time scales for black holes to accumulate such mass. But the presence of these ancient behemoths suggests that either black holes formed through a different process in the early universe or that there were precursor objects, perhaps from an era even earlier than what we can currently observe. Webb's instruments also detected signatures of heavy elements, carbon, oxygen, even possibly nitrogen, within some of these galaxies. The presence of such elements so early after the Big Bang was completely unexpected. According to established theory, the first stars, so-called population 3 stars, were made entirely of hydrogen and helium, the primordial elements formed in the minutes after the Big Bang. These first stars were supposed to live fast and die young, exploding as supernovae and enriching the surrounding space with heavier elements. Yet the galaxies Webb has found appear to already contain metals, suggesting that at least one generation of stars had already lived and died before these galaxies formed. This compresses the time scale for star formation and evolution to a degree that current models cannot yet explain. Further complicating the picture is the distribution of these ancient galaxies. They are not randomly scattered, rather, they appear in subtle filaments and clusters, suggesting that the cosmic web, the vast structure of interconnected galaxies and dark matter, was already forming much earlier than expected. This is one of the most significant implications of the discovery. The early universe was thought to be relatively smooth, with density fluctuations taking billions of years to grow into the large-scale structures observed today. but the Webb data hints that the seeds of cosmic structure were not only planted earlier, but that they bloomed with shocking rapidity. This accelerates the timeline of structure formation and forces cosmologists to re-evaluate simulations of the universe's early development. Adding to the complexity, Webb spectroscopic instruments picked up faint signs of ionized hydrogen and helium, suggesting that these galaxies played a role in reionizing the universe, the era when the universe transitioned from being opaque to transparent. This epoch, known as the era of reionization, marks a key phase in cosmic history, but its exact timeline has remained elusive. By identifying galaxies that are bright enough and old enough to have contributed to this reionization process, Webb has offered direct observational evidence for a process that has until now only been theorized. Webb's success in reaching the edge of the observable universe also opens a new frontier in the study of cosmology, the examination of cosmic variance and the question of whether the universe is truly homogeneous on large scales. While current cosmological models assume that the laws of physics are the same throughout the universe, the deep field images captured by Webb hint at subtle asymmetries and variations in galaxy formation. This raises the question of whether the cosmos is more complex and varied than previously assumed, possibly affected by early quantum fluctuations or unknown physical forces that operated shortly after the Big Bang. These findings are not just abstract scientific results confined to ivory towers, they alter the very narrative of how the universe began and evolved. If the early universe was forming stars and black holes much faster than previously believed, then the fundamental constants and forces that governed that era may have been operating under conditions very different from those we experience today. Perhaps the laws of physics themselves evolved over time, or perhaps there were initial conditions at the Big Bang that we have yet to comprehend. Moreover, the success of Webb in peering this far back has rekindled interest in questions once considered speculative: what lies beyond the observable universe? If the James Webb Space Telescope can observe galaxies at the very limit of what we can see, then perhaps future instruments, more sensitive, with greater resolution, might reveal even older structures, or even detect signs of physics beyond the known horizon. Some theoretical physicists speculate that these limits might reveal evidence for multiverse theories, extra dimensions, or even remnants of pre-Big Bang structures embedded in the cosmic microwave background. Another profound implication comes from the time aspect of this discovery. The light captured by Webb from the edge of the observable universe has taken over 13.5 billion years to reach us. When we observe these ancient galaxies, we're looking back in time to an era that no longer exists. These galaxies may have evolved, collided, or ceased to exist entirely. What Webb provides is not just a view of space, but a time capsule, a frozen image of cosmic youth. This temporal reach gives astronomers an empirical tool to trace the entire history of cosmic evolution from its earliest chapters, piece by piece. The technical achievement of capturing such faint and ancient light is also nothing short of extraordinary. The sensitivity and precision of Webb's instruments are orders of magnitude beyond what was previously possible. Its ability to maintain stable observations over days and weeks while oriented at a precise point billions of light-years away speaks volumes about the engineering marvel that it is. The coordination between ground control, data analysts, and cosmological theorists in processing and interpreting these images reflects the monumental scale of this achievement. As more of Webb's data continues to be analyzed, new surprises are almost certain to emerge. Already, hints of gravitational lensing around these early galaxies are allowing astronomers to glimpse even more distant, even fainter structures magnified by foreground masses. It's possible that buried within these observations are the first images of star clusters or even individual stars from the earliest stellar generations, each of them a beacon from a forgotten age. What makes this discovery so electrifying is not just that we now see farther than ever before, but that what we see defies expectations. The James Webb Space Telescope has not merely confirmed our models of the early universe, it has disrupted them, demanded their revision, and unveiled a cosmos more dynamic and mysterious than imagined. At the edge of the observable universe, where light meets darkness and time itself seems to stall, we now see the fingerprints of creation in sharper detail than ever before. The implications for future research are staggering. Scientists must now reconsider the parameters that define cosmological simulations, the models of galactic evolution, and even the nature of fundamental particles and forces. The earliest chapters of the universe's story have always been shrouded in mystery, but with this new data, the pages are beginning to turn, revealing narratives of unexpected complexity and grandeur. This discovery also deepens humanity's sense of cosmic perspective. That we can detect light from a time when the universe was less than 1 billion years old and analyze its contents in exquisite detail is a triumph not only of technology but of human curiosity. It brings into focus the profound scale of the universe, in time, in space, and in mystery. Every photon caught by Webb is a whisper from the ancient past, a message traversing eons to speak to a species just beginning to understand its place in the cosmos. There is a poetic resonance in the idea that, at the farthest limits of our vision, where the cosmos fades into darkness, the universe has chosen to reveal not silence, but wonder. Through the eyes of the James Webb Space Telescope, the cosmos is not a static canvas but a dynamic, ever-evolving theater of creation. The edge of the observable universe, once thought to be a boundary, now feels like an invitation to dream bigger, to ask deeper questions, and to reach farther into the unknown. If you like this video, please give it a like and subscribe to our channel. Also leave your comments below and tell us what are your thoughts on what James Webb found at the universe's edge. We want to hear from you. Thank you for watching and see you next time.